tell you guys a little bit about what this journey has been like for me. So we started off with this concept that we pitched to NASA in a grant proposal, where we wanted to put the space mirror version of the mirror surgical robot in an express rack locker, which is their standard experiment capsule, on the International Space Station, and try to see what it's like to do simulated critical tasks in microgravity and considering the latency it takes to get from space to ground from the ISS. So we proposed this idea to NASA, and thankfully they were supportive and funded this grant. And so in order to get to our final version of this payload, we built three prototypes, as I like to call it. The first one that you see on the left is pretty bare bones, not so much going on, but you can see a lot of similarities still carry over all the way to our third iteration. We oriented the robot diagonally in the locker. We experimented with several different types of surgical tasks that we would want to potentially do in space. And then you can also see that the cabling is exiting through the front of our box there. And that was something that carried through throughout this entire process. Our second prototype was fully functional, meaning that all the computer and hardware and electrical equipment was very, very similar to our final device. And with this, we were able to kind of perfect a lot of our code and computer programming that we needed for the ISS project. And then lastly, on the far right, you can see our ground unit, which is identical to the payload that we sent to space, except for instead of being sent to space, this one was used for testing. And this testing was needed to prove that the payload would be ready to send to space and that it would be safe for the astronauts to use. So in order to accomplish that goal, NASA provided a lot of help. We met with them weekly, and they provided feedback with engineers from all these different teams. So payload interfaces and operations. We had lots of software and safety integration meetings, and then we also had an input from human factors engineer to help us design what the user interface for the astronauts would look like. So this is the control panel that we ended up designing that one of the astronauts ended up using on the ISS. And there's some things that you might not think about when you're designing something to go to space. And one of those that I did not think about was labeling. And so it was definitely an interesting journey to talk with our human factors engineers and learn about all the different things you have to think about when you're designing something to be as easy as possible to use for the astronauts in space. We also had to include labeling on the inside of the payload, which you guys might happen to see in the exhibit. One of the things that NASA was pretty concerned about was the scissors on the robot device. They are blunt tip safety scissors. We wanted to make sure that there was no possible way that we had accidentally give an astronaut paper cut, as I like to joke. So you can see some of the labeling that we do there to make sure that everything went smoothly along with. Once we had finalized our design, including our labeling design, we moved on to the testing phase of this project. And there were several phases of tests that we needed to do in order to prove to NASA that we had met the requirements for both safety, but also a lot of the specific tests I'm going to talk to you about right now. The first one was power quality testing. And for this, we actually had to travel to Huntsville, Alabama to visit Marshall Space Flight Center there. They have the only power supply on Earth that is identical to what is on the ISS. And so in order to prove that our payload was compatible with the power supply in space, we had to go test the robot and the payload there in person. And thankfully, the engineers there were very supportive and helpful, and we were able to pass this test successfully during our trip. Another test that we had to do was electrical compatibility testing. So anything that runs on electricity emits electromagnetic waves. in the non-visible spectrum for the most part. And so you want to make sure that your missions do not interfere with other ISS systems. It's very important that everything continues to run smoothly on the ISS, and we did not want to be the payload that messed that up. So in order to do that, we took the payload to NCAA lab in Nebraska, and we were able to test in the enclosed chamber that they have there in order to see what levels of emissions our payload put out. And thankfully, we were able to also eventually pass this test, making sure that we'd be compatible with the ISS. And this was a very interesting experience for me, as I'm not an electrical engineer by training, so I learned a lot about what those guys do. Crazy stuff. Then we had to do vibration testing. And so, as you can imagine, going to space is pretty rigorous. You have to fly on a rocket, and that rocket ride can get pretty bumpy. So in order to make sure that our payload would survive the launch, we simulated a launch condition where the payload was vibrated on all three sides to prove that it could survive the rocket launch. And thankfully everything did, it did great. NASA was in particular concerned that the scissors wouldn't open during the launch, and so that was one particular thing we were paying attention to during this test. Another thing we had to do was acoustics. So we took the payload into a very quiet chamber and we measured the sound emitted while in normal operation. And in order to run the payload continuously, we needed to prove to NASA that the sound is below a certain decibel level for protecting the astronauts in hearing. And then also, I think, when you're on the ISS, there's no outside you can go to escape the high-pitched buzz sound that could be created. So we wanted to make sure we were quiet and weren't creating beats or anything. So that was kind of the purpose of this test, and you can see that we had the sound meter set up according to their guidelines and stuff to prove that the payload was good to go. And then once we satisfied all of our requirements, we actually shipped the payload off to NASA, and it waited a while until we caught a ride on the NG-20 launch earlier this year in January. This was a special launch because it was the first time a Northrop Grumman Cygnus spacecraft had been launched on SpaceX Falcon 9 rocket. And so it was kind of cool to be a part of that piece of history. The payload docked with the ISS on, I believe it was February 2nd. Of this year, and then we waited until we got unpacked and we were ready to go for our experiments. So this is a picture of the installation process. That's actually astronaut Laurel O'Hara installing the payload on board the ISS into an express route, where in order to get set up and ready to go, all we needed to do was get plugged in and then connected to internet. And we would be able to talk to the field and watch what was going on from Earth. So definitely this was an exciting moment for me in order to be able to talk with NASA mission control. I had to go through some training in order to learn how to use the radio speak that they have and the special software that they use to talk to astronauts. And then you can also see that we had the timeline of what all the astronauts were doing pulled up as well. So it was really cool to see live when they were ready to start putting our payload in. Then we began our deployment portion of the experiment. And so we had the robot cut some of our simulated tissue or the fancy rubber data, using the onboard computers and the payload to compare some data that we would get on Earth with computer control and then also in space. And so thankfully that test went super smooth. You can see everyone smiling in the picture. We're watching the robot do its thing. But after the autonomous experiment, it was time for the exciting part, which is the remote control section. And so this is a picture of us participating in that experiment. And this is where we had a surgeon control the surgical robot from Earth. So you the surgeon console, controlling the robot and cutting rubber bands while it is at those space. And there was some latency that we had to deal with conducting this experience, so that the surgeons had to be really on their game to make sure that that didn't phase them. But thankfully, everyone was able to successfully dissect their rubber bands and complete all surgical tasks that we had both, which was super awesome. We got lots of good data. And we also got to let me have a try, which I was totally not expecting. But I was able to dissect one rubber band without breaking the robot, even though I'm not a surgeon. And that was really special and kind of a full circle moment for me. At the end, Laurel and Howard helped us out again and uninstalled our payload and packed it up to get returned to us. And you can see we got historical photos of her and the robot, which was a pretty cool moment for me as well. And so now we're just waiting for the payload to come back, and I'm really excited to take a look at the data that we'll get back, so we can kind of compare the data that we collected on Earth with the data we collected in space, see what we can learn there. And then also, I'm really interested in the research units of the surgeons conducting this experiment and what latency was like for them, and if there's any tips that they have to share about what it would look like to do more post-surgery experiments in crazy far-off places in the future. So, thank you everyone,